Let's compute standard that's not right. Let's try this again. Let's compute standard deviation. Now that's correct. All right, so standard deviation is a measure of the typical distance a data value is from the mean. So this is what we use a lot to talk about the spread of data. If something has a small standard deviation, then the data values are clustered. If it has a large standard deviation, then it's really spread out. And to find it, standard deviation is the square root of the variance. So when we think about the formula, first let's talk about a population first. So a variance is x squared equals the summation of x minus mu squared, where mu is the mean. So data value minus the mean squared, add them all up, and divide by the sample size. Well, for a standard deviation, we just take the square root of both sides. So we have sigma equals the square root of the summation of x minus mu squared over n. So if you find the variance, then you can just take the square root. Similar for a sample. For a sample, we have s squared equals the summation of x minus mu squared all over n minus 1. And for a standard deviation, then we just do the square root. So let's go ahead and work through some examples. Find the population standard deviation of 5, 8, 10, 12, and 13. So I like to create a table because it keeps things organized. So my data values, or x, are 5, 8, 10, 12, and 13. So remember, the formula that I'm working with here is sigma equals the square root of the summation of x minus mu squared all over n. So if you notice in the numerator, data value minus the mean. So step one is I have to find the mean. Well, in this case, I add my 5 values together, 5 plus 8 plus 10 plus 12 plus 13, and I get 48. So 48 divided by 5 gives me 9.6. So that mean allows me to find the deviation, which is x minus mu. So that's my next column in the table, x minus mu. So I'm going to take my data value. I'll take 5 and subtract 9.6, and I get negative 4.6. Ooh, that's an ugly looking 6. Whew. And then I take my next data value, 8 minus 9.6, and I get negative 1.6. And then I take 10 minus 9.6, and I get 0.4. And then I take 12 minus 9.6, and I get 2.4 and 3.4. So I have my x minus mu column. Now, this is the deviation column. If I would add all of those together, I should always get 0. And I do, because the sum of the deviations is always 0. Okay, so third, you'll notice in the numerator, I need the x minus mu squared. So that's my next column. I'm just going to square the x minus mu column. And anytime you square something, right, you're multiplying it by itself, so it's going to be positive. So negative 4.6 times negative 4.6 is 21.16. So as I go through, 1.6 squared is 2.56, 0.16, 5.76, and 11.56. All right, so I've done item number 3. Now, this squiggly looking E thing in the formula means summation. That means we're going to add the column of x minus mu squared. So I'm going to sum those up, and when I add those 5 numbers, I get 41.2. Okay, now since this is a population, we're going to use n equals 5. So now we're ready to put this into our formula. Okay, so let's just put this right in the middle here. So sigma equals the square root of 41.2 over 5. Because the summation, right, the whole numerator is here. This is the numerator, and this here, 5, is the denominator. So 41.2 divided by 5 gives me 8.24. And then we take the square root of that. So sigma is, to the nearest hundredth, 2.87. Pretty small, right? So it means our data is fairly clustered together, which we can see it is. Okay, now let's do a sample standard deviation. And here we have 6 numbers. So again, I'm going to start with my table. 8, 12, 16, 17, 18, and 25. And the only difference in our formula is that we're going to take the summation of x minus mu squared all over n minus 1. So the n minus 1 is really our only difference. Okay, so step 1, we got to find the mean. So when I add 8 plus 12 plus 16 plus 17 plus 18 plus 25, I get 96. And 96 divided by 6 is a nice easy 16. So when I go to do my x minus mu column, I have nice easy numbers, and I'm also going to do the x minus mu squared column at the same time. I find doing those at the same time, it's a little quicker, and it kind of makes sense, because 8 minus 16 gives me negative 8, and negative 8 squared is 64. So it's kind of just a nice, easy right across. 12 minus 16 is negative 4, squared is 16. 16 minus 16 is 0, squared is 0, 1, 1, 2, and 4, and lastly, 9 and 81. So you can always double check that your variate or your deviation sum is 0. And then remember, our fourth step is to sum the x minus mu squared column. So when I do that, I add those together. 64 plus 16 plus 1 plus 4 plus 81, I get 166. And because we're dealing with a sample, we know that n is 6, so n minus 1 is 5. So in our formula, S equals the square root of 166 over 5. Because the summation, right, this part here is the numerator. And we want n minus 1 in the denominator, which is 5. So again, if you use the table, it keeps things organized. Okay, so when I take 166 and I divide by 5, I get 33.2. And then when I take the square root of that to the nearest hundredth, I get 5.76, which is a little bit larger, which means our data is a little bit more spread out. And that's calculating standard deviation.